Hi, this is Tzvi Rosen. Today we're going to be talking about trigonometric substitution, which is chapter 7.3 in Stewart's calculus. And we'll start off with the Pythagorean identities, and these we derived in the last lecture, but we'll go over them briefly here. We start off with a squared plus b squared equals c squared, where a and b are the legs of a right triangle and c is the hypotenuse. And then dividing in turn by c squared, b squared, and a squared, we get, you know what? This should be an a. C squared, b squared, and a squared, we get sine squared theta plus cosine squared theta equals 1, secant squared theta minus tan squared theta equals 1, and cosecant squared theta minus cotan squared theta equals 1. We don't really need this, so we'll just put it in parentheses. We're just going to use the first two. Okay, now these are going to be useful to us because when we encounter certain expressions in square roots, it'll end up giving a nice reduction if we sub in a different one of these trig functions for x. So for instance, if we have square root of 1 minus x squared and we sub in x equals sine theta, then we get the square root of 1 minus sine squared theta. Since sine squared theta plus cosine squared theta equals 1, this expression is equal to the square root of cosine squared theta, which is equal to cosine theta, assuming we restrict theta to values where the cosine is positive. The next expression, square root of 1 plus x squared, if we plug in x equals tan theta, then we get an expression square root of 1 plus tan squared theta equals square root of secant squared theta equals secant of theta. Again, we're assuming restriction to values of theta where secant is positive. Finally, if we have the square root of x squared minus 1, where x equals secant, if we plug in x equals secant of theta, then the expression becomes square root of secant squared theta minus 1, which reduces to square root of tan squared theta, or tan theta, and again, we still need these restrictions on what values of theta we're allowing. Okay, so now that we've made these choices of substitution, we want to be able to draw the right triangle associated to the variables. Okay, so when we say that x equals sine theta, we put the angle theta here, and then we analyze this equation. If x equals sine theta, well, we know that that's equal to opposite over a hypotenuse. So the simplest way to express that would be to put an x on this side of the triangle and a 1 over the hypotenuse. Using the Pythagorean theorem, the remaining side will be equal to the square root of 1 minus x squared. Okay. By the same token, when we plug in x equals tan theta, tan is opposite over adjacent. We have theta over here. And now we want opposite over adjacent to be equal to x, so that means we'll call opposite x again and adjacent 1. And then the hypotenuse will be the square root of 1 plus x squared. Finally, because secant can be written as hypotenuse over adjacent, we are going to set this angle equal to theta again. And now x will be the hypotenuse, 1 will be the adjacent, and this side will be the square root of x squared minus 1. Okay? Now all of these square root expressions are just derived from Pythagorean theorem, keeping in mind that the sum of the squares of the legs have to add up to the square of the hypotenuse. Okay, so let's use these new trigonometric substitutions to do this integral. We're asked to compute the indefinite integral of 1 over square root of 1 plus x squared dx. So the first thing we notice is this expression is 1 plus x squared. So what we just learned is that a useful substitution is x equals tangent of theta. Well, whenever we make a u substitution, in this case it's a little bit trickier, but the same idea holds. We want to express dx in terms of d theta, So we take the derivative of x with respect to theta, and that's just the derivative of tangent theta. So that's secant squared theta d theta. And we plug it into this equation. So this becomes, into this integral. This integral becomes the integral of 1 over square root of 1 plus tangent squared theta times secant squared theta d theta. Okay? And the other thing to remember is that there's a right triangle associated to this. So we're going to draw that quickly so we don't forget what we're thinking about. So there's theta here, tangent is x over 1, and this is square root of 1 plus x squared. So reducing this using Pythagorean identities, we have the integral of 1 over square root of secant squared theta d theta, of secant squared theta, and then secant squared theta d theta. Okay. Here we have a single power of secant theta, because the square root of secant squared is secant. And we're assuming that secant takes positive values for the values of theta we're interested in. So we're left with the integral of secant theta d theta. You might remember from one of the previous lectures that the integral of secant theta is ln of secant theta plus tangent theta plus c. Okay. Now, what do we do with this? Like, well, we want to get something in terms of x, because that's the variable we started with, but now we have this funny geometric expression in terms of theta. So what we do is we look at our triangle. So secant theta in our triangle is hypotenuse over adjacent, which is the square root of 1 plus x squared. And tangent theta is x. That was by definition. So we have this is equal to the natural log of absolute value of x plus square root of 1 plus x squared plus c. Okay? And that's our answer. This shows how useful subbing in with a geometric expression can be when you have these square root expressions. Okay, so the problems get more complicated when we consider extra constants. For instance, if instead of 1 plus x squared like we had in the last problem, we have 2 plus x squared or 3 plus 4x squared. So here there are two steps that I think will help us deal with this. First step is to factor out a constant from the whole expression so that the constant term is 1. And the second part is replace x by u equals ax so that it is a perfect square with coefficient 1. For example, in 2 plus x squared, my first step, as I mentioned above, factor out the 2, so now we have a 1 in the constant spot. Unfortunately, we have x squared over 2 here, so that doesn't look nice. But instead of writing x squared divided by 2, I can write 2 times 1 plus x over the square root of 2 squared. Okay, and these are equal expressions. And now instead of having x squared multiplied by a constant besides 1, here we just have a different square. And so the substitution I would make here would be something like x over square root of 2 equals tangent theta. Okay. How about with 3 plus 4x squared? Same approach. First, factor out the constant to make the constant term 1. So we factor out 3. 1 plus 4x squared over 3. And then you combine the constants in here to make a single square. So 1 plus 2x over the square root of 3 squared. Okay, and here you would make the substitution 2x over the square root of 3 equals tangent theta. Okay. Let's use this information about extra constants to evaluate this integral. So here we have the square root of 9 minus x squared. So looking at 9 minus x squared, I want to turn this into something like 1 plus or minus a square. So let's factor out the 9. So we have 9 times 1 minus x squared over 9. And I want to group this second term together so that it's a square without any coefficients. So I can do that by making 9 times 1 minus x over 3 squared. Okay? So looking at this expression, I know that this is a 1 minus a square, so I want this to turn into sine squared. So I make the substitution x over 3 equals sine theta. Okay. Given this substitution, we have dx over 3 equals cosine theta d theta. Equivalently, dx equals 3 cos theta d theta. Okay. So let's make the substitution, and we obtain square root of 9 minus sine squared theta minus, apologies. 9 times 1 minus sine squared theta divided by, okay, so here x squared is going to be the square of 3 sine theta, so that gives us 9 times sine squared theta. And then the dx is replaced by 3 cosine theta d theta. Okay, now let's simplify. This is the integral of, well, the square root of 9 is 3. So 3 over 9 will end up canceling. And we also have a factor of 3 over here, so 3 times 3 over 9. That'll all end up canceling. Times the square root of cosine squared theta divided by sine squared theta times cos theta d theta. This is equal to, well, obviously these constants cancel, and we're left with cosine squared theta over sine squared theta d theta. And this is equal to the integral of cotangent squared theta d theta. So we arrive at the integral of cotangent squared of theta d theta, and one way to integrate this is to use the Pythagorean identity, turning this into cosecant squared theta minus 1 d theta. And the antiderivative of cosecant squared theta is cotan theta. Cotan theta minus theta plus c. Okay, as before, now we have this expression in terms of theta, but we want to turn it back into x's. So let's draw a right triangle related to our substitution. So we had sine theta equals x over 3. So that means opposite over hypotenuse is x over 3, which I can take as x being the opposite and 3 being the hypotenuse. And if that's the case, then the other side is the square root of 9 minus x squared. Okay, so what's cotangent of theta in this triangle? Well, that's equal to adjacent over opposite, which is square root of 9 minus x squared divided by x minus theta, which, as we know, is arcsine of x over 3 based on our definition plus c. So that's the solution to this integral. Okay, here's one more practice where, again, we have a substitution which will require us to play with the constants a little bit. So here it's x squared plus 4. So we know it's going to be related to, we want it to look like 1 plus something squared. Let's call it y squared. So the first thing we do is we turn the constant into 1. So let's factor out our 4 and switch the order of the terms for our convenience. So 4 times 1 plus x squared over 4. And then we group the constants inside of the square, as we did earlier. So it's 4 times 1 plus x over 2 squared. And now we have the form that we're interested in, 1 plus something squared. So our substitution, our trig substitution, will be x over 2 equals tangent of theta. Okay, now let's go ahead and draw the right triangle right now. Oh, first let's get dx. So dx over 2 equals secant squared theta d theta. And the right triangle is going to be given by, well, tangent of theta means opposite over adjacent. So that's x over 2. And then this side is going to be square root of x squared plus 4. The hypotenuse is going to be square root of x squared plus 4. Okay. So now let's do the substitution. So we have the integral equals the integral of dx, over which we're replacing with 2 secant squared theta d theta, divided by x squared, which will be 4 tangent squared theta, times the square root of 4 times 1 plus tangent squared theta. Okay. So simplifying, we can cancel out one of the factors of 2 here. We're left with secant squared theta d theta divided by 2 tangent squared theta times, okay, and the square root of 4 becomes 2 times the square root of secant squared theta, because that's what the Pythagorean identity translates to. And further reducing, this secant squared theta becomes a single secant, so we get cancellation, and we're left with a single secant on top. And we're left with 4 tangent squared theta on the bottom. Okay, that's pretty good. So this unfortunately is not in the form that we're used to seeing with these secant and tangent integrals. So instead we might want to express this all in terms of sines and cosines. So let's pull out the 1/4. And then we have secant is 1 over cosine theta, divided by tan squared, which is sine squared theta over cosine squared theta d theta. Okay. Okay, and now I'm going to make a new page. And we will so we're carrying over this, this is the last step of our integration from above. So, hi, I noticed an error in the computation that was recorded earlier, so I'm going to record a correct version now. we were looking at the integral of 1/4 times the integral of 1 over cosine theta divided by sine squared theta over cosine squared theta d theta. And picking up from there, we can simplify this just by taking the reciprocal and multiplying. We have 1 over cosine theta times cosine squared theta divided by sine squared theta d theta. And that is carry down the 1/4. We cancel out 1 power of cosine, so we're left with cosine theta divided by sine squared theta d theta. And here a u substitution will be helpful. If we take u equals sine theta, we get du equals cosine theta d theta, which is exactly what we have on the top here. So we can do, let's correct that for. So we get 1/4 times the integral of du over u squared. And this is 1/4 times minus 1 over u plus c, or minus 1 over 4 sine theta plus c. We still want to turn this back into x variables. So looking back at our right triangle, we're going to borrow that. Can move this over here, and we do not need this too. Okay, so looking at this right triangle, if we want to know what sine theta is, we just divide opposite by hypotenuse, and we get this is equal to minus 1 over 4 times the opposite, which is x, divided by the hypotenuse, which is the square root of x squared plus 4. And we've got to remember the c. And this gives us, if we flip the fraction here, we get minus the square root of x squared plus 4 divided by 4x plus c. And that should be our integral. Okay, so far we've been doing indefinite integrals, but things get a little trickier once you're dealing with definite integrals. When the integral is definite, you have to make sure that the substitution is 1-to-1 on the interval of integration. For example, in the integral from 0 to 1 of 1 over square root of 1 minus x squared dx, if you sub in x equals sine theta, don't change the bounds to theta start equals 0 and theta end equals 9 pi over 2, because that doesn't map to the interval 0, 1 in a 1-to-1 way. Okay, because if you think about what the sine curve looks like, so going up to pi over 2, it goes from 0 to 1, and then it goes down again and up again and down again. And so if we're allowing values up to 9 pi over x equals 9 pi over 2, or theta equals 9 pi over 2, then you're going to get a lot of values hitting the same value between 0 and 1. So we don't want to allow that. Instead, we just take the last theta to be pi over 2. So if we limit ourselves to this range, we're only going to get one value of theta for every value of x, and that's exactly what we want. In general, it's sufficient to restrict theta to the interval minus pi over 2 to pi over 2 for x equals sine theta and x equals tan theta. Thinking about their graphs, sine theta looks like this between minus pi over 2 and pi over 2. And tan theta looks like this. There's vertical asymptotes at minus pi over 2 and pi over 2. Okay. For x equals secant theta, we'll want it to be restricted to 0 to pi over 2, because secant theta looks more like this. It also has asymptotes at minus pi over 2 and pi over 2, but it's symmetric. Okay, so you want to limit yourself to 1/2 so that the values are still 1 to 1. The map is still 1 to 1. Okay, let's evaluate a definite integral. We're going to take the integral from 0 to 3 root 3 over 2 of x cubed divided by 4x squared plus 9 to the 3/2 dx. Okay, so what the 3/2 thing means is it's the square root cubed. So we're looking at a square root of 4x squared plus 9. So we're going to want it to look something like 1 plus y squared at the end, right? Because this is a sum. So what we'll do is, as before, 4x squared plus 9, we first factor out a constant to make the constant term equal to 1. So we have 9 times 1 plus 4/9 x squared. Okay, and now we want to group x together with a constant to make it a simple square. We get 9 times 1 plus 2x over 3 squared. Okay, so looking at that, we say that we want to sub in tangent theta equals 2x over 3. Okay, because we want to have 1 plus tan squared theta. And that means that secant squared theta d theta equals 2/3 dx. Okay, and another way of writing that would be dx equals 3/2 secant squared theta d theta. Okay, so I'm going to quickly erase this. So subbing in for this integral, we're going to have, instead of x cubed, we're going to have 3/2 tan theta cubed. And on the bottom, we'll get 9 times 1 plus tangent squared theta to the 3/2. And then the dx will be replaced by 3/2 secant squared theta d theta. Okay. So let's start simplifying. On the top here we have this cube of 3/2, so we can pull that out. 3 cubed over 2 cubed, and then we'll just be left with tan cubed theta. We get another 3/2 over here, so I'll just add that in, times 3/2. And on the bottom, we can take 9 to the 3/2 is also 3 cubed, so 1 over 3 cubed. Okay, we're clearing out all of the constants. And we are left with secant squared theta, tangent cubed of theta, divided by secant squared theta to the 3/2. Okay, and there I made the substitution, 1 plus tan squared theta equals secant squared theta. And we have d theta. Okay, combining all of these constants, we get 3 to the 4th over 3 cubed is 3, divided by 2 to the 4th, which is 16. Okay, the secant squared theta cancels with the secant cubed theta on the bottom here to make tan cubed theta divided by secant theta d theta. And at this point, we observe that we start with a definite integral. Okay, and we really should have brought bounds into this problem. And the way that we would have done that was by evaluating what theta would give us 0 and what theta would give us 3 root 3 over 2 if we plugged it into this. So we know that tan theta equals 2x over 3, or x equals 3/2 tan theta. So if we take theta equal to 0, we'll get x equals to 0. So that can be our lower bound. Well, when x equals 3 root 3 over 2, that means tangent is root 3. Okay, so tangent theta equals root 3 when theta equals, and this is something you can check in your chart of the unit circle, this is when theta equals pi over 3. So this goes up to pi over 3, 0, pi over 3, 0, pi over 3. Okay, now let's bring this integral to the next page. So we have 3/16 times the integral of tan cubed theta over secant theta d theta, where theta goes from 0 to pi over 3. Okay, well, again, this isn't the secant tan that we're used to, so we're going to express everything as sines and cosines. Yeah, let's do that. Okay, so we're just replacing tan with sine over cosine and secant with 1 over cosine. And reciprocating and multiplying, we get 3/16 integral from 0 to pi over 3 sine cubed theta divided by cosine squared theta d theta. And here we're able to, and what we'll do here is we'll use a Pythagorean identity to rewrite this as sine theta times 1 minus cosine squared theta divided by cosine squared theta d theta. Okay, one final u substitution will close out this computation. We'll take u equals cosine theta, and then du equals minus sine theta d theta. Okay, as for evaluating at the endpoints, we have u of 0 equals 1, cosine of 0 is 1, and u of pi over 3 is 1/2. Okay, let's plug that all in. So we get 3/16 times the integral from 1 to 1/2 of 1 minus u squared divided by u squared times minus du. And we pick up a minus sign here because it's minus sine theta d theta as opposed to sine theta d theta here. Okay. Now simplifying, we can pull out the minus sign, put it with the 3/16. We have 1 to 1/2 of 1 over u squared minus 1 du. Taking the antiderivative, minus 3/16 of minus 1 over u minus u from 1 to 1/2. We can change all of these minus signs to pluses, and we have 3/16 times 2 plus 1/2, which is 5/2, minus 1 over 1 plus 1, which is 2. So this is just 1/2, and we're left with 3 30-seconds. Okay? And that integral was a lot of work. We had to do a couple of variable changes, but at long last we got there. Okay, the final example for today is a little bit more abstract. Compute the area of the ellipse x over a squared plus y over b squared equals 1. And we're going to assume here that a and b are positive numbers. Let's not even allow it to be equal to 0. Just strictly positive. Okay, so let's think what we're actually computing an integral of. So what does an ellipse look like? Well, this ellipse, it's centered at 0, 0, and it has values a0, a0, 0, minus a0, and 0 minus b, 0, b. So it looks something like this, where this is a and this is b. Okay. So if we want to compute the area of this ellipse, we want to compute the area under some curve. It'll be easiest to just compute the area under this curve. And then we just multiply it by 4 and get the area of the ellipse. So the area that we're interested in is 4 times the integral of the function describing the ellipse, dx, where x goes from 0 to a. Okay, but what is that function describing the ellipse? We can use this equation. So y, if we have x over a squared plus y over b squared equals 1, then that means that y over b squared equals 1 minus x over a squared, which means that y is equal to b times the square root of 1 minus x over a squared. Okay? So we know this is equal to 4 times the integral from 0 to a of b times the square root of 1 minus x over a squared dx. Okay? So now comes the trigonometric substitution. We see here this is of the form 1 minus a square. So we want to substitute x over a. So let's sub in x over a equals sine theta. Okay, if that's the case, then dx over a equals cosine theta d theta. And in terms of the endpoints, the boundary points, we have the x value corresponding to, the theta value corresponding to x equals 0 is just theta equals 0. And the x value corresponding to a, well, when x over a is sine theta, a over a equals 1, so theta should be pi over 2. Okay. So let's continue where we left off. We have, actually I'll just grab this part. Okay, that's a little better. Strange. Okay. So we're in the middle of this substitution. And we have, after making the substitution, we have 4 times the integral from 0 to pi over 2 of b times the square root of 1 minus sine squared theta times a cosine theta d theta. Okay? So first things we can do, a and b we know are constants, at least relative to x, so we can take them out. So we have 4ab times the integral from 0 to pi over 2 of square root of 1 minus sine squared theta. Well, we know that's the square root of cosine squared theta. That's why we picked it. Times cosine theta d theta. And this is equal to 4ab times integral from 0 to pi over 2. Here we just get a single power of cosine times the other cosine, gives us cosine squared theta d theta. Okay, well we have an identity associated to cosine squared, which is cosine squared is equal to 1/2 times 1 plus cosine 2 theta d theta. Okay, so let's pull out the half, and now we're left with 2ab times the integral from 0 to pi over 2 of 1 plus cosine 2 theta d theta. And that's equal to 2ab times theta plus 1/2 sine 2 theta, evaluated from 0 to pi over 2. And we get 2ab times pi over 2 plus 1/2 sine pi, which is just 0, minus 0 plus 1/2 sine 0, which is also 0. So it's 2ab times pi over 2, or pi a b. And that's intuitively what it should be. Think about, for instance, when a equals b. Then what we have is a circle. If a equals b equals r, then this is pi r squared. And that confirms what the area of the circle should be in terms of the area of an ellipse. Okay, so we were able to do a bunch of cool stuff with trigonometric substitutions, a lot of integrals that we would not have otherwise been able to do. And like with all of the other tools for integration, it's just a matter of practice, finding the trig substitution, carrying it through to the end, drawing your right triangles when necessary. Okay, thanks so much.